Hello everyone, I am going to present AOWS Adaptive and Optimal Width Search with Latency Constraints, a joint work by myself, Maxim Berman, as well as Leonid Pishchulin, Ning, Blaschko, and Gerard Medioni. We are interested in calibrating the width of each layer in a neural network. For instance, in this simple 3-layer neural network, we can use low number of channels, which leads to fast inference but poor accuracy on the task. Or we can use more channels, which leads to better accuracy but a slow inference. We want to minimize the error of the network delta of n while maintaining the latency of the network under a fixed target LT. Our first goal is to estimate the error delta of the network for a given configuration of channels. In principle, this would require an entire training of the network with that channel configuration. However, we develop a simple scheme in order to obtain an indication of this error. To this end, we train a slimmable network by varying the channel configurations at random for each image during the training. We estimate the error caused by the choice of a channel number in a particular layer by averaging over the losses that were obtained when making this choice during training. By summing these estimates over all layers in the network, we obtain our estimated error for a given configuration of the channels. Using a Lagrange multiplier gamma, we add the latency constraint to obtain our final objective. Moreover, we observe that the latency of the network is the sum of the latencies of each individual layer. The latency of one layer depends primarily on the number of input channels and on the number of output channels of that layer. This is why our latency model decomposes additively over pairs of channel choices. The great thing about this objective is that it can be solved very efficiently using the Viterbi algorithm. Using multiple iterations of this algorithm, we can also adjust gamma in order to obtain a solution that satisfies our target latency, following the principle of Lagrangian optimization. But how exactly do we obtain this pairwise latency model? On their own, layer operations perform quite differently than when inserted within the whole network. This is why timing individual layers in a network is hard. Instead of attempting to do so, we time entire networks with varying channel configurations. We then fit the individual layer latencies in order to best explain our observations, using a least square solver. Our experiments show that this method leads to very accurate latency models under the inference modalities that we have used, such as NVIDIA TensorRT on GPU. This summarizes our optimal width search algorithm, or AOWS. We first train a slimmable network by sampling configurations uniformly, and then we use Viterbi decoding to determine the optimal channel configuration satisfying the constraint. We propose an additional refinement of AOWS called Adaptive AOWS or AOWS. It relies on the intuition that during the training of the slimmable model, many sampled configurations are not interesting to us. They have either high latency or they correspond to high estimated error. For this reason, we progressively bias the sampled configurations towards good configurations according to our objective. This is done by using a continuous relaxation of the Viterbi algorithm and sampling according to the resulting probabilities. This procedure has a temperature parameter that we reduce towards 0 over the course of the training. We experimented with the MobileNet V1 architecture with 14 channel choices per layer. We compare mainly with AutoSlim, which also uses slimmable networks but uses a greedy selection procedure rather than our Viterbi-based algorithm. We target the NVIDIA TensorRT inference engine on GPU. Our experiments show that under the same latency target, the AOWS algorithm reaches higher accuracy than the greedy selection procedure of AutoSlim. Moreover, the adaptive sampling approach of AOWS further improves on this accuracy by progressive refinement of the search space. Finally, we show that our results are competitive with other published architectures found with neural architecture search in low latency settings. We also experimented with CPU and GPU latency targets without TensorRT and reached similar conclusions with respect to the improvements of AOWS over the greedy selection procedure. Thank you for your attention. For more information, don't hesitate to reach out.